Welcome back. And in this lecture, what we're going to cover is one of the important influences on the climate system, which is volcanoes. And volcanoes are really important factors that have influenced climate mainly on timescales of 1 to 2 years, but also can have bigger long-term impacts. And the impacts of volcanoes are associated with what they emit into the atmosphere, particularly associated with particles and dust and sulfate. So volcanic debris, big volcanic eruptions, put a lot of dust and a lot of sulfur into the atmosphere. But it doesn't just sit in the lower atmosphere, it gets lifted up with big explosive volcanic eruptions into the upper atmosphere, the layer called the stratosphere. And that dust and particles can reflect sunlight back out to space. It reduces the amount of sunlight that gets through to the surface of the Earth, and that leads to global cooling. And the dust and particles typically last for between 1 and 3 years. And in fact, they also lead to wonderful sunsets. And so the major volcanic eruptions that have occurred are, when they're strong enough, can inject debris, dust, and then sulfur dioxide and then sulfate aerosols into the atmosphere long enough to have a cooling impact. When we look at the observational records for the last 100 years, we can see associated with all the very big volcanoes cooling in the climate system for about a couple of years. And we can also see that when we run climate model simulations, that as we would expect, more particles in the upper atmosphere leads to cooling of the climate system. And I'm going to show the results for that in just a couple of minutes. The really interesting thing is that about 75,000 years ago, there was a supervolcano, the strongest volcano that we have both geological and observational evidence in the last million years. And this led to a prolonged cooling of the climate system for a period of, well, hundreds of years. And that indicates that if we had a massive supervolcano, it can have a big impact on the climate. This is actually a way that we can test climate model simulations. If they can simulate the observed changes in volcanoes, it's a way of evaluating the performance or the response of climate models and testing how good they are at simulating the future climate. But the other thing that's been suggested is, look, if volcanoes can emit particles into the upper layers of the atmosphere, into the stratosphere, and cool the climate system, maybe if we as humans could use some technology to get particles into the upper atmosphere, and enough particles, then maybe we'd be able to offset some global warming. So right at the end of the lecture, I'm going to talk about what's called geoengineering, some of the different options that are being talked about, and in particular, is it feasible to inject particles into the upper atmosphere to cool the climate system, and what might be some of the impacts, good impacts and adverse impacts. So let's look at the observed temperature variations. This graph was shown in the climate modelling lecture. I think that was the previous one. And what we see is these vertical lines show the major volcanic eruptions that have occurred since 1900 in the 20th century. The most recent major volcano was Mount Pinatubo in the Philippines. There was also El Chichon in Mexico in 1982. Pinatubo was in 1991, El Chichon was in 1982, and Mount Agung in 1963. And really interesting thing is that if we look at the observational data, you'll see that there's pronounced cooling in the observations associated with each of these volcanoes. And then if we look at the climate model simulations that are shown, there's also, in the average across all the climate models, a pronounced cooling in the models. That is, some cases a little bit less than the observed cooling, in some cases a little bit more than the observed cooling, but generally the climate models simulate a cooling that lasts for about 2 to 3 years after these massive volcanic eruptions, for Mount Pinatubo, for El Chichon, and for Mount Agung. Now, these don't show some of the really big volcanic eruptions like Krakatoa in the 19th century, in the late 1800s. And what we're now going to look at is the evidence for this massive volcanic eruption that happened about 75,000 years ago. And Mount Toba is a region, now a lake in fact, in Indonesia, that erupted, best evidence is around about 70 to 75,000 years ago. And there's lots of evidence for massive changes that occurred associated with this volcanic eruption. It's probably the biggest volcanic eruption in at least the last 100,000 years. There's evidence of reductions in ocean temperatures, particularly in high latitudes, by about 10 degrees C, using evidence from ice cores in Antarctica. There's evidence from changes in the biological sediments. There's evidence of changes in the amount of ice debris in the North Atlantic. So this was a global cooling of the climate system for thousands of years associated with this major volcanic eruption. And we can see evidence for the size of this volcano when we look at the crater lake that now exists in Indonesia for Mount Toba. So here's where it's located in Indonesia, and we can zoom in on this region, and this is the crater lake that exists, and it's more than 30 kilometers across in this direction and more than 100 kilometers from north to south. So this is a massive amount of debris that would have been injected both into the lower atmosphere but particularly into the upper atmosphere, and it led to a cooling of the climate system for an extended period. And to see the evidence for that cooling, these are temperatures from ice cores in Antarctica, and here at 70,000 years ago we see a pronounced cooling of the order of 5 degrees in ice core evidence in between the temperatures that we see in the modern period, the Holocene period, and the previous warm period in the interglacial period 120,000 years ago. Right in the middle, around 70,000 years ago, we see an abrupt 5 degrees cooling that lasted for thousands of years. And that is best associated with the eruption of Toba. The eruption of Toba then injected this massive amount of dust and sulfur into the upper atmosphere, reflected sunlight and led to this prolonged cooling, and then the growth of the ice and snow reflected enough sunlight for that to last for 1,000 years approximately. Now, that then provides evidence that maybe, in addition to mitigation, reducing greenhouse gas emissions or adapting to climate change, there's been another suggested response to climate change. Geoengineering is the term that's used, and geoengineering is really just engineering components of the Earth system, of the climate, to try to reduce the warming influence of increasing greenhouse gases. And there are a number of suggested options, and really the first one that's been suggested is increasing the amount of particles that reflect sunlight. So we have what's called a negative radiative forcing, or a cooling influence, by reducing the amount of sunlight that's received at the surface of the Earth. And there are a number of different ways that this can be done, but the one that's been suggested is artificially injecting particles. Aerosols in this case mean small particles injected into the stratosphere, just like a volcano does. Now, volcanoes are an example, and Mount Toba is also an example of where injection of these particles can cool the climate system for an extended period. Now, what's being suggested is that maybe we could use big aircraft like jumbo jets, 747s, to carry large amounts of sulfur particles or sulfate aerosols into the stratosphere, inject them out of the aeroplanes into the stratosphere, and we could use a fleet of aeroplanes to do this. It's technologically feasible now to do it. But the real question is, well, okay, that might reduce the warming, but what are the adverse impacts? So increasing particles in the atmosphere reduces sunlight. reducing sunlight slows down the hydrological cycle, and it does it in a more rapid way than the impact on cooling the climate. So the impact of reducing sunlight on the hydrological cycle slows it down, and that means less rainfall in the tropics. And that means semi-permanent drought, slowdown in the monsoons in almost all tropical countries. The other impact of aerosols is they act as sites for the photochemical destruction of ozone. So if there are more sites on these particles in the stratosphere for the photochemical destruction of ozone, this is going to lead to increased ozone depletion. And then the increases in ozone depletion are then going to mean more ultraviolet radiation being received now, not just in Antarctica, like with the Antarctic ozone hole, but in lower latitude regions, because these particles will exist in all regions across the climate. We see evidence for this ozone depletion associated with every major volcanic eruption. And if we use geoengineering to put particles in the atmosphere, we're going to get more UV radiation, and that means more skin cancers on people all around the world. So what we're going to have is less monsoon rainfall, less rainfall in the tropics, more skin cancers, and in addition, even if we do this geoengineering by injecting particles, we're not going to reduce the carbon dioxide that's being injected into the atmosphere, or we might not, which means still we're going to have more carbon dioxide in the oceans, which is increasing ocean acidity, and that's going to have major impacts on marine life. So what we're going to do, potentially, if this was seen as the solution, is dramatically change rainfall in the tropics, kill more people with skin cancer, and increase ocean acidity and reduce marine life. That doesn't seem like a very sensible solution. While geoengineering by injecting particles might reduce the symptoms of climate change, it doesn't address the ultimate cause. But there are some other suggested geoengineering solutions, and actually one of them is to reduce carbon dioxide more quickly by fertilizing the oceans, increasing ocean uptake of carbon dioxide by stimulating plankton growth in the oceans. Phytoplankton are small plants that take up carbon dioxide through photosynthesis. They're limited in many regions by the lack of iron. So iron can be injected potentially into ocean waters. Then that will lead to what's called a phytoplankton bloom, which can take up more carbon dioxide. Of course, it's unclear how sustainable this is, and in particular, experiments that have been done show a short-term increase in uptake, and then it saturates and you don't get a long-term increase in carbon dioxide uptake. There are other suggestions, like increasing carbon dioxide uptake by planting more trees on land, or increasing carbon dioxide uptake in soils, or even through carbon capture and storage, capturing carbon dioxide before it's emitted from power plants that are using fossil fuels. There are even some really way out suggestions, like changing the reflectivity of land, maybe putting white plastic sheeting on land to reflect more sunlight. But if you work out the area that this would have to be done, it's impractical. And the other wacky suggestion is, well, maybe we could put out into space large reflectors, like satellites, but covering a large enough area that it reflects enough sunlight. But in practice, what we would need to do is to reduce the amount of sunlight by a fraction of 1%, because that's the amount of energy that we're going to have to do. Its best estimate, it might be as much as 1%. And if we're going to reduce the sunlight by 1%, that means we have to effectively reduce, with a sunshade, 1% of the area of the Earth. And that's a massive area of reflector if we're going to put it in space. And there is no technology that could put that amount of reflector out in space. The advantage, potentially, of doing it with aerosols is the particles get redistributed all around the atmosphere by the winds in the stratosphere. So while geoengineering by injecting particles is potentially feasible. We have the technology to do it. There are many, many adverse impacts. And so, while it's a potential response, it's actually preferable to reduce the impacts of climate change both through mitigation, reducing greenhouse gas emissions, and through adaptation. So, volcanoes. Volcanoes like the Mount Toba volcano are a great indicator of another factor. The injection of particles into the atmosphere reducing sunlight, therefore leading to a cooling of the climate system. We can also see this every time there's an intervening shorter-term volcanic eruption. Now, this then suggests that maybe these injection of particles, aerosols into the atmosphere, and then scattering sunlight and reducing the amount of sunlight received at the surface of the Earth might be a possibility for addressing climate change. But before we can do that, we have to answer the question, will the solution through geoengineering be worse than the problem that it's trying to solve? And certainly for injecting particles into the stratosphere, it appears that the adverse impact from injecting particles could well be much, much worse than the problem of climate change. And it's actually better, probably, to address climate change both through mitigation, reducing greenhouse gas emissions, and adaptation. And I'm sure there's going to be much more discussion of the economics and the potential for solving climate change in later lectures. Thank you very much.